Hello, and welcome back to part 2 of this video, where we are going to be doing our second parter, where we are going to be looking at gas law stoichiometry using the ideal gas law specifically. So we're going to be balancing chemical equations and going through the step-by-step process of how to read word problems, digest them, and break them down in these different problems. So in part 1, we focused on STP related problems. So these are going to be a little bit trickier. We'll be going through how to essentially balance problems. So going through tips and tricks behind that, how to read word problems and to digest them in your introductory chemistry course. And we're going to be looking at exactly how do you identify when to use the ideal gas law, when to use partial pressures, and how to go through even limiting reagent problems, focusing on gas laws. So this is a very comprehensive guide on how to solve these. Thank you so much for stopping by. If this is your first time here, hit that like button and comment below if you have questions. So let's go dive into these and let's try to figure out all about this type of problem. But when it comes to the ideal gas law, this is always referring to what the current condition is of the gas after the reaction occurred or even before the reaction occurred. So what is the condition? Now, the big thing about this is you have 4 different variables, which are pressure, volume, temperature, and moles. You need 3 out of 4 of these to be able to use this formula, or it can get a little bit tricky and a little complicated. So generally, you're always given 3 out of the 4. So when we are looking at these, we are going to be exploring all the different formulas in many different problems. So let's take a look at how to use these starting with STP. All right, so our first problem in part 2 is we're going to be looking at the stoichiometry of the same problem we ended with in part 1, which was involving the oxidation of glucose within our body. So one thing about it that we learned last time is that glucose is broken down, and as a result, we breathe out CO2. So this is one of the most common reactions that we see. So let's take a look at this problem and how we are going to digest it. All right, so stoichiometry with the ideal gas law. So if I take the same chemical equation like I had before, and I ask you this time to calculate the volume of carbon dioxide gas produced when you have 24.5 grams of glucose and it's consumed at body temperature, so 37 degrees Celsius, and at 0.970 atmospheres. So let's go through the problem. How would we do it? What would we start with? Well, the first thing you always want to check is, do you have a balanced chemical equation? Which we do, right? It's the same one from before. The next thing is you want to look through your problem and kind of identify all the key bits of information, right? We have essentially how much glucose we have our temperature, and then we also have what our pressure is. But we're asked to figure out the volume. So you have to reorganize the ideal gas law and get all the different pieces that are required. So let's kind of go through and see, do we have all the correct units here? Well, the first one that I can kind of spot out at the bottom here is that pressure is in atmospheres, which one way to always check yourself is, does it match the units of your ideal gas constant, right? So you can see it's liters, moles, atmosphere, Kelvin. So we have atmospheres. We got one down. Let's look at temperature, right? Temperature is at 37 degrees Celsius up here at the top. So does that match your temperature here? And you can see that it doesn't. So we need to now convert temperature to Kelvin. So what we'll do is we'll take 37 degrees C, add to 73.15, and what you're going to get is 310.15 Kelvin is your temperature. So now that one's good. All right, now what about moles? Well, moles is what we can actually get with our glucose, right? So we have 24.5 grams of glucose in the problem. So being that we need to convert that to moles of CO2, right? Which is our gas. That's the thing that most people mess up when they do this problem for the first time, is they try to just get the moles, right? Which is great, but you need to make sure that it is your moles of your gas. That's really important. It has to be moles of your gas. So if we were to do the same step as before, right, from our previous problem, we'll divide this by the molar mass, which was 180.15 grams of glucose. And that's equivalent to 1 mole of glucose. And now what we're going to now do is get it to moles using our chemical equation, right? And it's for every 1 mole of glucose is equivalent to 6 moles of CO2, right? So 1:6 ratio. Let's write that down, right? 1 mole of glucose, and that's equivalent to 6 moles of CO2, right? So 6 moles CO2. All right, now we want to check that our units cancel, right? So we see grams of glucose cancels grams of glucose, great. And then we can also see moles of glucose cancels moles. So we're in the right unit. So that means we have our last piece once we calculate this. So when we put all this into our calculator, you'll take 24.5, divide it by 180.15, times that by 6, and what you should get is 0.8159595 moles. And keep in mind, you generally don't want to round this until the very end of your problem. It's usually very standard practice for most chemistry problems is round at the end. So now we have our moles, which was our last piece of the puzzle. So what we're now going to do is take our ideal gas law and plug everything in, okay? So let's do it. So what do we have? Well, we have our first number, which is our moles. So let's take that. So we're going to copy that number. We're going to paste that down here. And let's kind of change our color to kind of match here. So we got blue and blue. Now we'll take our R constant, which is in red. So that is 0.08206. So you can see that at the top of your screen. And then we're going to times that by the temperature, which was 310.15. And I apologize for not putting units into this, but it's also saves space. And then we're going to divide all that by 0.970 atmospheres. Okay, so that's going to be on bottom. And then we're going to divide everything. All right, so when we put all that into our calculator, we'll take 0.8159595, times that by 0.08206, times by 310.15, it equals, then divide by 0.970. And what you're going to get is 21.4 liters as your final volume for this number, right? So that is our answer and how we do these harder problems, okay? Let's take a look at the next one. Sometimes with stoichiometry and the ideal gas law, you will also have to use Dalton's law, which is the law of partial pressure, meaning that if you add the pressure of each individual gas together that's in the container, the total pressure will be all of them added up. So let's say if I were to do this experiment, which all of my students have done, all the students at my school do in terms of the introductory chemistry, is essentially you take a metal, you react with HCl, you collect gas. So let's say if we want to look in that farther. So hydrogen gas is produced when aluminum metal reacts with hydrochloric acid. A sample of aluminum produced 511 milliliters of H2 gas, which is collected over water at 300 Kelvin and 745 millimeters of mercury. Determine the mass of aluminum reacted. And then we have the partial pressure of water here. So of H2O that is here. So with all those pieces of information, what exactly are we going to do? Well, I wrote out the steps to help map out the problem. The first thing you need to do with this type of longer stoichiometry problem is we need to predict and balance the problem. After that, we want to write down all the given numbers to see like, okay, we want to convert everything to the ideal gas units. Remember, our goal is the mole. So then we want to make sure we get our moles, and then we want to convert to our final units. So that's a lot of steps to remember. So let's break this problem down one step at a time. Okay, so predict and balance. So with this one, I essentially took out the excerpt from what was important, which was the first line. And what it says is that hydrogen gas is produced, okay, when aluminum metal reacts with HCl. Now, it doesn't mean that it's every ingredient here, but it does give you a hint at what essentially is reacting together. So that tells you that the product was H2, which is one of the products. Now, it also says that you have aluminum reacting with HCl. So one thing when you're trying to predict these is you got to be able to recognize what are the different types of reactions by writing down what your individual recipes are. So in this case, we have A plus B, C, meaning that A is going to kick out B to do a single replacement reaction or single displacement. So in this case, what is your displaced part? Well, that's going to be hydrogen. And the other thing is aluminum is going to react with chlorine. Now, whenever we predict a reaction, we do not bring any subscripts with us. There weren't any to begin with, but you need to make sure you write down your charges because they need to be swap dropped, right? So meaning that the 3 from aluminum needs to come down and become a subscript for chlorine. So we're going to take a 3 and put it right down here at the side. Now, with that, all the subscripts are good, but you'll see really quickly is that this is not a balanced reaction. So the tip that I have in the top left corner is we should even the odds, just like we said earlier. Where can we start? Well, one thing you can see is that I have 3 chlorines on one side and I have 1 on the left. I also have 2 hydrogens and 1 hydrogen on the left as well. So how exactly can we try to balance those? So if I think of evening the odds, if I put a 3 on the left, well, then they're both odds. That doesn't really even it out. So what's the next best number to choose? Well, if I put let's say a 2 in front of aluminum chloride, making 6, which is now even, and now I put essentially a 6 over here in front of HCl, also even. And what does that do is, well, that evens the odds. It evens that that odd subscript, which is crucial. Now, what can we do from there? Well, our chlorines are balanced. What about our hydrogens? Well, I have 6 on the left. How many do I have on the right? I have 2, right, that are right here. So what can I do there is I can put a 3 in front of that. That's balanced. And now what about aluminum? And we can see, oh, that's not quite balanced. So let's fix that for ourselves. So 2 aluminums reacts with 6 HCl to make 2AlCl3 and 3 hydrogens. So we got to balance the problem, right? And you always want to check in case you overbalance, like can you reduce the numbers? Like can I divide them all by 2 or by 3? You always want to check. In this case, you can't. Let's take a look at our next step. All right, you want to now write down all the given values, convert them to the units that you find in PV is equal to nRT. So what you need to match your ideal gas constant. So let's write everything down in the problem. So the first thing that we had is that a sample of aluminum produced 511 milliliters of gas. Now, if you remember, the ideal gas law constant needs to be in liters. So what we're first going to do is convert that to liters. So 511 milliliters is essentially equivalent to 1,000 milliliters is 1 liter. So we'll divide by 1,000 and we'll have 0.55 liters of H2 gas. Okay, so that's part of it. We have 300 Kelvin, so that one's okay. So we can write that down as well. And we also have 745 millimeters of mercury in the problem too. So do we want to use that pressure though? Because that's telling you what the total pressure is. It's not referring to the gas we're interested in or what we have information on. All the information that we have in this problem, for the most part, is referring to, especially the volume of the gas, is H2 gas. So if that is H2, what we need to do is essentially find the pressure of H2. So let's take our partial pressure up here. So take our formula down. And what we are going to do is rearrange it to solve for the pressure of H2. So if I were to do that, right, we can see that, well, if the pressure of H2 is on one side, essentially what we need to do is subtract the pressure of water to get the pressure of H2. So we got to rearrange our equation. All right, and I'll put the original one back up here just so you can see, right, we subtracted the water from both sides is what happened. Now, we were given the partial pressure of water, which was at 24 millimeters of mercury. So what we'll do is take the 745 millimeters of mercury, then we'll subtract 24 millimeters of mercury. And what we're going to do is convert this to atmospheres. So this entire number here, we're going to divide by 760. So when you get your 721 millimeters of mercury, you'll divide that by 760. Now, when we have that, what we are going to essentially get in the end is 0.948684 atmospheres, which is going to be your pressure. Okay, so our liters, we have our temperature, and then we have our atmospheres. We have 3 out of the 4 conditions required to use the ideal gas law. So now with that, that's what we're going to do next. As for our last step, is we're going to plug all these into the ideal gas law to solve for moles. Because remember, our goal is the mole. So if we were to do that, let's take our numbers. So we have our N value, right? So we'll copy that down. And our N value, our pressure value. And that's going to be multiplied by, in this case, by the volume, which was at 0.511. Let's try to color code these. So we have 0.511. We'll make that pink to match. 0.511 liters. And that's going to all be divided by R, right? Which we have right here on the side. So that's 0.08206. And then that's going to be multiplied by the temperature, which was 300 Kelvin. So let's take that value and bring it down. Now we're going to plug all that into our calculator. So you're going to take 0.948684 times that by 0.511 liters. And then you're going to divide that by 0.08206 times that by 300. And what you will get is 19692 moles of hydrogen in this problem, right? So are we done? And the thing is, the last part was all about, well, can you convert this to aluminum, right? What is the mass of aluminum in this problem? So here we have the moles of hydrogen. So now we got to do our last step, which is using the balanced chemical equation that we started with. This is a very, very long and tough problem when we have to go through all these steps. So with that, right, we are going to take 0.019692 moles, and we are going to essentially convert that to our moles of aluminum. So using the chemical equation. So we have moles of H2, and we can use the chemical equation to see that, okay, for every 3 moles of H2, so we'll write that down here, and that's equivalent to every 2 moles of aluminum on the left-hand side. Okay, so it's a 3 to 2. Now, when we do that, we can see that moles of H2 cancels moles of H2, but we want it in mass. So how do you go from moles to mass? Is we have to use the molar mass to do that, which we have from our periodic table. So with that being said, we'll take that 1 mole of aluminum from the periodic table is equivalent to 26.98 grams of aluminum. All right, so now that we did that, we will take our calculator, we'll take our mole value, times that by 2, times that by 26.98, and divide it by 3. And what you are going to get is 0.354 grams of aluminum, which is your final answer. Because you started with 3 significant figures, we have to round it to 3 significant figures. And that's how you do the entire process. So with stoichiometry, this can be as tough as it gets. Really, the only thing that can really go even farther than this is if you do a limiting reagent problem, which is our last problem. So let's take a look. Limiting reactant stoichiometry can be some of the toughest problems that we can ever see in stoichiometry. Now, how do you identify them? Let's take a look. So with this one, it says how many liters of HCl are produced from 25 grams of BaCl2 and 0.250 liters of 0.1 molar H2SO4 at 1 atmosphere and 300 Kelvin. So we're mixing a liquid with a solid to make a gas. Oh, this is combining everything together. So the way that you can tell that it is a limiting reagent problem is when you essentially have 2 starting ingredients and it lists their amounts. So here we have 25 grams, and you also see that you have the entire concentration of the solution with its volume, which is really important to keep in mind. If the volume is not there, you probably are fine, but it needs to have both components. So now the other part about it is it doesn't mention doesn't give us the formula either. So we have to first start with just balancing. So we have barium chloride and sulfuric acid mixing together. So when we do this, we got to first remember inside out. So we will do the inside and the outside will bond together. So now, as I said before, you don't bring the subscripts. So we'll take just H plus and Cl minus. Notice how they're already balanced, so you don't need to swap drop. And then you have barium 2 plus and then sulfate 2 minus. We bring the ions. All right, now you see that they're both 2s, so that means they're the same charge, so they cancel each other out. We are good and balanced in terms of charges. Now, is the chemical equation balanced? Let's take a look. Well, this is where I say start with the polyatomics and do what I refer to as the zigzag method, meaning that when I look at here, we see we have sulfate on the left and right. We have one on the left, one on the right. Great. So now let's take a look at zig over to H2. We have 2 on the left, and now we're going to look and zag to the other H, and we see that we have 1. They are not balanced. So let's put a 2 here. Now they are. So as a result, I'll now look at chlorine, and we can see that, hey, chlorine is now balanced. We have 2 and 2. And if you look at the barium, you can see that's balanced as well. Everything balanced when you zigzag back and forth. So now that we have that, let's go to our next step. So from this part of the problem, remember our goal is the mole. So we had these different starting ingredients. We had 25 grams of barium chloride and 0.25 liters of 0.1 molar H2SO4. So what's the first thing you should start with? Well, let's start with the barium chloride, being that that's by itself over here. So if I were to take that number and I were to just drag it down, how can we convert it to moles, right? That is our entire idea here, is we want to get it to moles of HCl because that's the gas we're interested in. So what we need to do is to convert grams to moles is use the molar mass. So we have 208.23 grams of BaCl2, and that's equivalent to 1 mole of BaCl2. And now we're going to use our chemical formula, which is 1 mole of BaCl2 is equivalent to 2 moles of HCl. All right, so now that we have that in moles, we're going to stop there. So I'm going to show you a way to make these problems 10 times faster, is we just want to get 2 moles. So now our grams cancel. Great. Now, when we are to solve this, what we are going to end up getting is we'll see that we have 0.240 moles of HCl that is possibly made if all the barium chloride is used. So let's now go do the other part. Well, now with this one, it's always tricky to do solution stoichiometry. Always start with the volume because it's a term by itself. So when we do that, we can actually cancel it using molarity as a conversion term, right? Molarity is moles over liters. So meaning that we have 0.1 mole, and that's equivalent to 1 liter of H2SO4. Okay, so we'll put 1 liter. And as you can notice, is that, liters cancels. Great. And now once again, we'll use the chemical formula, which told us that 1 mole of H2SO4 was equivalent to 2 moles of HCl. So let's add that here. So we'll have essentially 1 mole H2SO4 on the bottom, 2 moles of HCl on the top. Okay, and then once again, you'll see units cancel, just what we want. All right, so now when we do the math, we'll do 0.25 times 0.1 times 2, and what we will get is 0.0500 moles of HCl. Now, what we are now going to do is we got to compare the two numbers, the one that we have all the way on the top right of the screen, and then the one that we have all the way on the bottom of the screen, the one in purple and green. So if you compare them, which one is smaller? And the thing is, you're going to see the one next to me is a lot smaller. That means that this ingredient ran out completely. It didn't react as much as the other one did. So this is your limiting reagent in this case, right? So we want to put a big LR here to tell us, hey, this is our limiting reagent, which means H2SO4 ran out. So this is the calculation you want to finish or use in terms of the last step. So we're going to use this to figure out what our final volume is. All right, so now we have our ideal gas law. We listed all of our values out. So we want to use our limiting reagent mole value, which was 0.05. We will use our ideal gas law constant, right, which we plugged in as well. We have our temperature value as well, which we'll use too, which is 300 Kelvin. And then it's all going to be divided by our pressure, which was 1 atmosphere. Now, when you put all this into your calculator, you're going to take 0.05, times that by 0.08206, times that by 300, and you will have a volume of 1.23 liters. Okay. So you do not have to use the ideal gas law twice, is what this is trying to tell you by cutting this shorter. You just have to see which one has less moles, right? And that you can do that for any limiting reagent problem. You can even do it for mass stoichiometry too, or solution stoichiometry. It saves you a little bit of time. That wraps up the end of part 2 of this video series. I hope that this helped you understand a little bit better gas law stoichiometry. As you saw, that it can get a little bit complex, but with more practice, you can master this. So if you need any help, please reach out to me, talk to me. If you see me on campus, come say hi. If you are someone just viewing this video, please feel free to comment below and ask questions. I'm always checking to reach out to help students just like you. And if this is your first time here, please hit the like button and subscribe to the channel for more introductory chemistry, organic chemistry, and biochemistry content. All right, y'all. I hope you all have a wonderful day, and I'll see y'all later. Bye now.